Hey, welcome back to another exciting example of Mr. Warnow does your homework! Alright, hey, before we begin, I do want to talk a little bit about slope fields for a little bit. Since we're talking about slope fields, we tend to see slope fields all the time in the real world. An example of a slope field is a weather map. If you look at a weather map like so, you have a bunch of high pressures and you have some low pressures, but I want you to take a look at these lines right here. Now these lines are called contours. And what basically they have, this is a good example of a slope field. Basically saying that if I want to find the weather on a particular place on a map, if I go on this contour, well, in this case, the pressure everywhere on this contour is going to be exactly the same. We have many different contours or slope fields on this map right here, but everything in this line is going to have the exact same pressure. If I go to this point right here, we can find the pressure at exactly on this contour right here, or this slope field. Now next year in multi, we're going to talk a lot more about these contours and even maybe solve for a couple of them, kind of like what we're doing right now with slope fields. But other examples, we do see contours in magnetism. You might recall slope fields in magnetism. You might recall back in elementary school or in high school, you took a magnet, and you put some metal shavings on a table, and you got all these little field lines, right? This is a magnetic field, or a slope, or in math we call it a slope field. If anything comes on this line right here is going to stay on this magnetic field line. Again, another example of where we see slope fields. We have lots of different fields right here, but if you drop a metal shaving and it lands on this line, it's only going to stay on that line. Now, where do we also see this? The Earth. The Earth has magnetic field lines as well. Any particle coming in from the sun will hit these magnetic field lines, and they travel along this magnetic field line and go to the poles, North Pole or the South Pole. And that's where we get the aurora borealis from, or the southern borealis, the northern lights or the southern lights. And they come from these magnetic field lines. And the movement that they make is because of the way the particles interact with the magnetic field of the Earth, or slope fields of the Earth. And we can actually find out where these are. Interesting thing happened about these magnetic field lines. I think it was in the 1950s, the U.S. wanted to find out how magnetic field lines would interact with a nuclear weapon. So what scientists did, they launched in the Pacific, in a very remote place in the Pacific, they launched a nuclear missile into space, and they exploded it. And you can actually see this on video. They videotaped it, people standing underneath it, and you can see the explosion. It's like brighter than the sun. Anyways, when the nuclear missile exploded in space, they found out something very unique. The explosion traveled along these magnetic field lines, and it caused blackouts all along this magnetic field lines. And people in Hawaii noticed, they didn't know what it was, and the government kept it a secret for years. But it was basically how the magnetic field or the slope field affected the Earth itself. So scientists found out a lot about that, and they actually use that now. Like if they want to do a nuclear war, if they would launch a nuclear missile, explode it and they know about these magnetic field lines. So what they would do, they would launch a missile now, explode it in space along a magnetic field line, and they can knock out the power in certain parts of the world. Very easy to do. All right. Anyway, so that's just like where we kind of see these in the real world sometimes. All right, so let's take a look at some examples from your homework. Now, for your homework tonight, you have these to do. Okay, you're gonna do a bunch of these fields, these problems here. They do take a while, but I want to take a particular look at number 6 real quick, just to kind of talk about this idea of division by zero. Zeros are always a little bit hard. So if I have a division by zero is hard. So if we look at the one right here where we have y over x. Well, let's see what happens if we let y equal 0. Oops, there we go. If we let y equal 0, well, what's going to happen? Well, if I let y be 0, my dy dx, x could be anything. We're not going to mess with 0 or 0 yet. It's going to be 0 over x, which is just 0. we're going to get a bunch of horizontal lines. So basically, where y is 0, we're going to get a bunch of horizontal lines. And here's where y is 0, a horizontal line, horizontal line, horizontal line, horizontal line, horizontal line. Notice I didn't put anything in the center there. We'll talk about that. If we let x be 0, we get dy dx becomes negative y over 0. Well, that does not exist. That's undefined. So what type of line is that? Well, that's going to be our vertical line. So where x is 0, we have a bunch of vertical lines. Now notice again, I didn't put anything in the center. So let's talk about 0, 0. What if x and y both equal 0? Well, in that case, we get dy dx is 0 over 0. And you might recall, this is what we call indeterminate. Oop, ran out of room. Indeterminate right there. So how does indeterminate affect us? We don't put anything there. Nothing goes there. Nothing goes here. We just leave it blank. We leave it blank. The worst thing I've seen students do, they want to do this. Well, it's both horizontal and vertical. No, you put that, it's going to be wrong. We just, whoops, there we go, erase it. We just leave that a blank space, okay? Don't write anything when you have 0 over 0. All right, so let's take a look at example like number 7 right here. These aren't too hard to do. We'll take a look just at a few of these. So we want to find out which of these slope fields matches the function, matches the derivative for dy dx is sine of x. Well, if these are slope fields, well, we know from experience what sine of x looks like. Sine of x is wavy gravy. Well, which one of these looks like sine of x? Or it could look wavy gravy like a cosine function, right? Or a sine function, a trig function. And of course, the only one that kind of matches that is c. Take a look here. It goes down, up, down, up, down, up. Yeah, so this is going to be c. Oops, hold on. If we look at 8, this is a tough one. We saw this in our notes, if you paid attention. Also, it's very similar to, what's it, number 3, right? So, if you have a hard time, though, you can always just pick points. If I pick the point 1, 1, what's my slope going to be? Well, if I go 1 minus 1, it's going to be 0. So I know at the point 1, 1, the slope is 0. Well, I already know it's not going to be c. So if I look here at the point 1, 1, it looks like it could be 1. So A is a possibility. Not, if I go over here, 1, 1, B looks like it could be a possibility. And if I go to D, 1, 1, oh, sorry, they're not possibilities. The slope has to be 0, not 1. That's so silly of me. Sorry about that. So A can't be a possibility. Excuse me. If I want the slope to be 0 at 1, 1, 1, 1 cannot work. See, the slope here is 1, not 0. Sorry about that. At B, the slope is also not 0. It's 1. It looks to be about 1 up here. So it can't be B as well. So the only other choice that we have, 1, 1, there. Look at here. It looks like the slope there is 0. So the only choice is D. And I can do the same thing for all these. Look at number 9. If I pick a point, ready? Pick point 1, 1. Or I'm only interested in y value. My slope would be 2 minus 1, which is 1. So of the two that I have left, it can't be D, remember. If I go to 1, 1, my slope here looks to be 1. And the slope here also looks to be 1. So it looks like it could be A or B still. So I just pick another point. Let's do 0, 0. That looks like they look both different at 0, 0. My slope here would be 2. Well, if I go over here, 0, 0, I do look like I have a slope here. 0, 0, my slope here is 0. So the answer is going to be A, because here at 0, 0, the slope looks 0. So it's not going to be B. And of course, by default, this would be B. Another one we can look at, this is parabolic. This looks like a parabola right here. So if I were to solve this derivative, dy dx, dy equals x dx, we would get y equals x squared plus c1, which is a parabola, so it has to be B. Very easy to do. And we can try a whole bunch of these. Try these ones as well. This one, which one does this look like it could be? Does it look like your x? No. So here's like kind of the opposite, right? Which one does it look like? Does it look like a parabola? This is a slope field. Now remember, a slope field is the graph of the function, just the graph of all of the functions. Graph of all functions. It's like a parent function, like a bunch of parents. Like it'll look like all this. So if it was a parabola, it'd be like a bunch of parabolas, like up here. There it is. All right. So coming down over here, let's take a look here, and you can just go ahead and answer this one too. It's the same. It's the same kind of concept. Which of these functions would look like the graph for number 16? And then you go, of course, you're going to have solving some differentials right here. Check your answers on my website if you need to. I will see you all later. Hope you enjoyed the video. Bye-bye.